Back, and now it's time to learn a little bit more about physics. So I think that you can understand what a bar magnet is, but the question is, what causes the magnetism inside of a bar magnet? So a bar magnet has a north pole and then it's got a south pole. So what's causing the magnetism inside of a bar magnet? Well, if you could look at the atoms that makes up the iron inside the bar magnet, you would see that the atoms are spinning. So an atom, it has a nucleus, and inside the nucleus it's got the protons, the neutrons, and then the electrons are in orbit around it. Now, protons are electrical, and we said that electrical materials can make magnetism. The electrons are electrical, and so they can make magnetism. Now, there's two different ways of making magnetism. One is if this electrical object is spinning, and another kind of magnetism is that if this electron is going around and around because it's orbiting the nucleus. Well, it turns out that it's the spin that's the most important. And so in iron turns out to have 4 electrons, and those 4 electrons can spin in the same direction, so that iron is naturally magnetic. So any iron atom is a natural magnet that goes with it because of those spinning electrons that are in orbit around the nucleus of the iron atoms. Okay, but the problem is that you have what's called a domain, and this is a clump of atoms that are all spinning in the same direction. Okay? Now over here is another clump of atoms, and let's pretend that these are spinning and they make little magnets that are pointing in this direction. Well, can you see that the magnetism in here could be canceled by the magnetism over here? So most of the time, if you've got a chunk of iron, it's not a magnet. If you take a paper clip and you try to pick up another paper clip with it, it's not going to work. So the iron has the capability of being turned into a magnet, but it doesn't, normally it's not, because these domains, these groups of little magnets, are not aligned correctly. Now, let's take one of these groups like this, and we're going to put it in an external magnetic field. So there's your external magnetic field, and now what will happen is if we heat up this piece of metal, the atoms begin to vibrate, and they will vibrate so hard that all of these little things are going to all start to line up with that external magnetic field. Okay? Now, there's lots of iron inside the earth, lots of nickel, and so these materials can get incorporated into the minerals that make up the rocks that make up the inside of the earth. And so if you've got these minerals and they are very, very hot, so they're all kind of like in the liquid form, and you put them in the exterior magnetic field of the earth, then as they start to cool off, they will align themselves with that external magnetic field, and they will become frozen in place, so that certain minerals in certain rocks have remnants of the magnetic field that existed when they formed. So when those rocks initially formed from magma, they will have little magnets inside of them that will align themselves with the direction of the magnetic field that existed back then when they formed. So, how can we use this? So when a geologist goes out in the field and they find some rocks, sometimes those rocks will have magnetic materials inside of them. And then when they take it back to the laboratory, they can measure the amount of magnetism in those rocks. They can measure the direction. So do you remember that you had let's go back up to here. You had the declination was the direction that the magnetic field was at that point, and then you also had the inclination was the amount that it would dip. So they can, in the laboratory, they can determine what was the direction of the magnetic field when those rocks formed, and they can plot it on a piece of paper. And do you see that squiggly line there on the Earth's surface? So that shows where was the south magnetic pole when those particular rocks were laid down. Okay, now they go across the ocean, let's say, into Europe, and they find the same set of rocks that they found in North America, and they measure the magnetism that's in those rocks, and they get another squiggly line, and you'll notice that the two squiggly lines, they don't match up. So the squiggly line from North America doesn't match with the squiggly line of Europe, unless you get out some scissors and you cut out North America and you cut out Europe, and you start to move them around, and so you move them until those two squiggly lines line up on top of each other, and then it will show you where were the continents with respect to each other. So it's a pretty fancy way of doing it, pretty difficult, but you can use magnetism in order to predict where were the continents located at in the past. Okay, we're going to take a break, and when we come back, we're going to use magnetism to show that the ocean spreads.